Hello everyone. Today I would like to introduce you all with the Seeing Theory website. This website is designed and created by Mr. Daniel Kuning of Brown University. The goal of this project is to make the statistics more accessible to a wider range of students through interactive visualizations. It has like 6 chapters. As you can see, it has like 6 chapters, but for this session, we're only going to cover the first 3 chapters, that is from basic probability to the probability distribution. The first chapter, that is basic probability, has like 3 subtopics, that is chance, events, expectation, and variance. If you click, go to the basic probability, they have some precise definition and explanation regarding this basic probability. The first is a chance event, and it says like, for the probability theory is a mathematical framework that allows us to analyze chance events in a logically sound manner. That is, for example, for the coin toss, the number is always between 0 and 1, where 0 indicates impossibility and 1 indicates certainty. When you there's a theoretical probability of a coin toss, that is like we are either assured to get like head or either assured to get the tail. That is the probability of getting tail is like 0.5 out of and the probability of getting head is like 0.5. But when you flip the coin, that is here, when you click this button, then flip the coin for 100 times, you can see the probability of getting head and probability of getting tail is changing. For now, from 100 flips, we got 57 tails, and from 100 flips, we got 43 heads. It says that as we keep increasing the flips, the chances of getting heads will be closer to 50%. And next, second, we have expectation. Expectation of a random variable is a number that attempts to capture the center of random variable distribution. And in a mathematical formula, it says expectation of x is sum of x and the probability of x. The blue line represents the expectation. When you roll the die for the first time, this is the average value, and expectation is 3.50. The expectation comes from here. The probability of getting 1 out of 6 is like 1 by 6, that is like 0.17, and same with the 2, 3, and 6. So when you do like 1 into 0.17 plus 2 into 0.17, we're gonna get our expectation, that is 3.5. And when you roll the die for like 100 times, you will see that our average is coming closer to the expectation, that is 3.50. And third, under the basic probability, we have variance. Variance, it provides a measure of centrality. The variance of random variable quantifies the spread of that random variable distribution. Mathematical formula of the variance, that is expectation of the random variable x minus expectation of x to the square 2. So the green, when you draw this graph, you see the average. The represents the average, and this represents the variance in blue color. And when you try to toggle this graph, you can see that how the variance is changing. And let's go to next chapter, that is compound probability. And under the compound probability, we have set theory, counting, and conditional probability. This compound probability further discusses the concepts that lie at the core of probability theory. So this is a Venn diagram. The set the set, and it's defined as the set is nothing but it's collection of the objects. So using this set constructor, we will try to form a set. So when you select A intersection C and click the submit button, you will see the this new portion that is represented with a yellow color, that is A intersection B. Or if you want to do like A B union C, it's the blue color, that is green is B and blue is C. You will see the union represented with yellow color. And next we have compound probability. Under the compound counting, we have the permutation and combination. Permutation is the ordered sequences, and the combination is like unordered state. So it says from a back of a marble, in which each marble is a different color. If we draw marbles one at a time from the back without representation, how many different permutations or the combinations can be formed? Right now we have selected 4 marbles, but for under permutation, if we try to select the second box, that is A and B marbles, you can see that our permutation is like A and AB or BA. But we have 2 sets, that is that if you can see this table, it says for 2, n is 2, that is like this is 1 n and this is n and 2, and we have a permutation of n of r, which is 2, that is A, B and BA. And if you select this third box, that is A, B and C, and if you can click this box, when you click this box, you can see the n is 3, that is 1, 2 and 3, and the permutation is 6. But when you click on the combination, the table will also change its value. That's under 3, we have n is 3, that is 1, 2 and 3, but for combination, we just have 1. This is combination. Conditional probability. So under the conditional probability, it says it allows us to account for the information we have about our system of interest. Example, it says the probability that it will rain tomorrow in general to be smaller than the probability that it will rain tomorrow, given that it's cloudy today. This later probability is a conditional probability. That is, it's only going to rain tomorrow because it's cloudy today. Mathematically, it is represented using this sample space. This is the sample space. The right portion is the sample space. When you click on A, you can see how the sample is shrinking, and when you click on B, you can see how the sample space is being shrunk. So this chart says the probability of A, given that B has happened, will be like 0.50, and the probability of B, given that B has already happened, will be like 1, and the probability of C, given that the B event has already happened, is like 0.50. And we have the next chapter, that is probability distributions. Under the probability distribution, we have random variables, discrete and continuous, and the central limit theorem. So what is random variable? It says the random variable is some real number that we try to assign to each outcome in the probability space. So this is a probability space, and if we for now, let's try to give keep our random variable as 3, and let's assign this value, that is random variable, to this space. We can click or we can drag. But after we're done with the dragging, you can submit this button. So you can see the orange color is the random variable, that is 3, that we have assigned to the probability space. So now this chart says in order to see the empirical distribution of our random variable, that is 3, we can click this sample distribution. You can see that it's not changing. It says our empirical distribution for this our random variable 3 is like 0.37. Next, we have a discrete and continuous probability distribution. The discrete is a discrete random variable has finite or countable number of possible values. That is, the probability of x is equals to small x, and this whole thing is equals to f of x, that is a non-negative function. But if probability of capital X is less than x, then it will be equal to this capital f of x, this is non-negative. The f of x here is represented by yellow color, and the orange color, it represents the capital F of x. So from this drop-down menu, we can choose one of the discrete probability type. For now, we're going to choose this Bernoulli distribution. Under the Bernoulli distribution, it says the random variable takes the value 1 with probability of p, and it takes value 0 when the probability is 1 minus p. So when you click on this, we can click this orange button and see how, see the Bernoulli distribution of this chart. You can also click this positive and negative button to shrink the space. Here, when you try to increase the value of p, you can see how the value of 1 is changing. And under the continuous, it takes continuous random variable takes an uncountably infinite number of possible values. It the x is a continuous random variable, then there exists like two non-negative functions like before, f of x and f of capital F of x. And the continuous also has like its own type, and it's uniform, normal, student squared, or exponential. For now, I will skip this part. I won't go into details. Then third chapter under the probability distribution is like central limit theorem. The central limit theorem states that sample mean of sufficiently large number of IID, that is independent and identically distributed random variable, is approximately normally distributed. For example, and this is from the draw. We're gonna give some sample space. Let's keep it to 3, and no, I will keep our draws to 2. And when you click the sample, you can see that we have 2 bar graph. But when you click the sample for the second time, it's 50. There's 2 bars count will be equally distributed with a new bar. So this is a central limit theorem. And thank you. I hope you. And if you have like any confusion or you want to know more, you can always go to this seeingtheory.brown.edu website. Thank you.